Hi everybody, how are you? I was about to call Dennis. If you are curious, Dennis is a good friend of mine. We call him the nerd. So he studies a lot, he reads a lot, and once in a while we actually meet and study together. I haven't seen him for a while, and I just wanted to call him and ask him how his weekend was. So let's call him and see what he says. Hi Dennis, how are you? How was your weekend?
My weekend was good. I solved hundreds of differential equations. I also watched your videos. I like the ones with Laplace Transform, but I strongly suggest that you discuss an overdamped system in your next video.
Okay, I promise you, I'm just going to go ahead and shoot a video about an overdamped system, and I will solve that using Laplace transform. See you later, Dennis. Bye. Yes, so on our channel, we already discussed Laplace transform, and we even solved a problem, a circuit problem, RLC circuit. It was an underdamped system using Laplace transform. So today we will make Dennis happy, and we will solve a problem which is going to be an overdamped system, and I'll choose a mechanical system, and of course we will use Laplace transform. So let's assume there's a spring attached to a mass m, and this is the equilibrium point. So x is equal to 0 is my equilibrium. Let's assume there is a drag force acting on the system. So at any given time t, let's say the mass is moving to the right, and this is my positive x direction. So there will be a drag force. So the drag force is given as minus b times v, okay, in this problem. And there is of course a spring force f of s acting on the mass, okay, and that's actually it. So here are the initial conditions. So let's say at t is equal to 0, x is x naught, and the velocity is equal to 0. So what happens is initially I pull the spring to the right, and then I just let the system go. So initially I'm at a distance x naught from the equilibrium point. My initial velocity is 0, the system is at rest, and then I let it go. And I want this system to be overdamped. Okay, so what does that mean? We do not want to see any oscillations. So when we solve for x of t, we don't want to see any sine or cosine functions. So there will be no oscillation. The damping is going to be strong enough that there will be no sine or cosine functions in the solution. So when I let the system go, it's going to move to the left, and then it's going to stop somewhere. Okay, so we are not going to see any back and forth motion. We are not going to see any back and forth motion. This is important. Okay. So now let's write down the equation of motion. So there are two forces acting on the system on the x-axis. Of course, there are forces on the y direction, but they simply cancel each other out. So the normal force balances the weight. Now we are ready to write down the equation of motion. There are two forces acting in the negative x direction. So these are minus kx minus dv. So this is due to the Hooke's law, force due to the spring. So this is equal to F net actually, net force acting on the system at any given time t. So this is equal to mass times acceleration. Okay. So if we write it in a different way, so this is the second derivative plus b times v is dx over dt, the first derivative of x. Then we have plus kx is equal to 0. So at this point, if we divide by m all the terms, so you have b over m and k over m. This is good. For those who already studied simple harmonic oscillation, so k over m is nothing but square of the natural frequency of this system. So if there was no damping, by the way, the first derivative term is the damping, right? So if there was no damping, this system would just oscillate back and forth. And the oscillation frequency would be square root of k over m. Okay? So that's why this is special. So I'll call b over m as alpha for simplicity. So you can call it like damping factor. Okay? So in the end, this equation turns into this. So alpha omega naught square times x. So we would like to solve this using Laplace transform. Okay. So let's move on from here. Okay, in the end, we have this second order differential equation that we would like to solve, and we will use Laplace transform. So as a quick reminder, the Laplace transform of cosine hyperbolic and sine hyperbolic functions are given like that. And we also have the frequency shifting property. So for those who haven't watched the Laplace transform video, I'll put the link under the descriptions. Please watch that video first, where we discuss all the details about the Laplace transform. And actually, why do I need these functions? Because I have an overdamped system, so I do not want to see any cosine or sine functions in my solutions, but I will have cosine hyperbolic and sine hyperbolic functions. Okay, and we will also use this later on. So when we take the Laplace transform of this equation, we have the Laplace transform of the derivatives. So we also discussed that in detail. So I strongly recommend that you go ahead and watch those videos first. Okay, so when we take the Laplace transform of this, so by the way, let's assume the Laplace transform of x, function x is given as f of s. Okay. The Laplace transform of the second derivative here is given as s square f of s minus x when t is equal to 0 minus, so there's s here, minus dx over dt when t is equal to 0. And the Laplace transform of dx over dt here simply equal to s times f of s minus x when t is equal to 0. So based on our initial conditions, this term is simply equal to 0. And x naught is simply a constant, so this is a constant. Now we can write down the Laplace transform of this equation based on these. So we have the second derivative, which is s square f of s minus s x naught, this is the constant, then plus alpha term, alpha, the first derivative, s f of s minus x naught, then plus omega naught square f of s is equal to 0. Okay. So now we can take f of s parentheses. So we have s square here, it's the first term here, and then I have plus alpha s, this term here, plus omega naught square. Okay, and this term is gone. So what's left is minus s x naught and minus alpha x naught, which is equal to 0. Good. So the next step is to write down f of s as a function of s. But before that, we can actually complete the squares here. Okay, let's do that first. So it seems like we are missing some terms here, so let's figure out what they are. So if I take the square of this, I get s squared plus alpha s plus alpha squared over 4. Okay? So wherever I see s squared plus alpha s, I can write s plus alpha over 2 squared minus alpha squared over 4. And this is what I will do here. So f of s, parentheses. So we have s plus alpha over 2 squared minus alpha squared over 4 plus omega naught squared. So this whole thing must be equal to s plus alpha x naught. So x naught times s plus alpha. Now we can write f of s. So f of s is equal to x naught s plus alpha divided by s plus alpha over 2 square minus. So here I have, if we put it in the common parentheses, alpha square over 4 minus omega naught square. Okay. Okay, so at this point, I will call this omega 1 square. So as you see, this looks like the Laplace transform of cosine hyperbolic and sine hyperbolic functions, as long as this term has a minus sign and this is positive, right? So we have minus k squared. So I will have minus omega 1 square here. Okay, so if this is the case, then we will not see any sine or cosine functions in our solution, right? Okay, so this is really crucial here. Now we can say that alpha square over 4 minus omega naught square, which is equal to omega 1 square, this is larger than 0. And this is the condition for the system being overdamped. Okay, so the system is overdamped under this condition. Okay, so we will move on from here. Okay, so far we found the Laplace transform of x of t in terms of s here, and we define omega 1 square as alpha square over 4 minus omega naught square. So as a common trick, we make this alpha over 2 plus alpha over 2. Okay? So when we do that, this f of s becomes, the first term is x naught, so I will have s plus alpha over 2 all divided by s plus alpha over 2 square minus omega 1 square. Then I will have plus, I have x naught alpha over 2 1 over the same term, s plus alpha over 2 square minus omega 1 square. Okay? So this looks like, the first term looks like the Laplace transform of cosine hyperbolic function. However, the second term kind of looks like the Laplace transform of sine hyperbolic, but I am missing one omega 1 here, right? This k over s square minus k square. So I will just multiply this with omega 1 and divide it by omega 1, so this is 2 omega 1 here. Okay. So now if I take the inverse transform, what we get is actually x of t. So x of t is simply equal to x naught. I can use the common parenthesis here. They both have x naught. So the first term is nothing but a cosine hyperbolic function, right? So cosine hyperbolic omega 1 t. But there is a phase shift. Instead of s, I have s plus alpha over 2. Okay, so this gives me an exponential decay term, e to the minus alpha over 2t. Okay, and plus I will have alpha over 2 omega 1, and I will actually have the same frequency shift here. So I can take this e to the minus alpha over 2t out. Let me write it down here one more time. X naught minus alpha over 2t. Use a common parenthesis here. So this also has a coefficient alpha over 2 omega 1. The rest is just sine hyperbolic omega 1 t. Okay, and this is actually the solution. So here one may ask, okay, cosine hyperbolic and sine hyperbolic has exponentially growing terms, right? E to the omega 1 t's, and omega 1 is positive. So both cosine hyperbolic and sine hyperbolic have e to the omega 1 t terms, okay? So these are kind of exponentially growing, right? However, this decay term here takes care of that. Why? Because I know that alpha over 2 is actually larger than omega 1, right? So this decay here is actually stronger than any exponential growth here. So when you look at the limit, when t goes to infinity, you will see that this term goes to 0. Okay? So if you wait long enough, you will see that the system tends to go back to the equilibrium, and then in the end it's going to stop. So you can also take the first derivative of this and see how the velocity changes. Just to give you an idea, I took some values for k. Let's say k is equal to 9 newtons per meter. So I put some values put a value for b, newton seconds per meter. I took mass to be 1 kilogram, and I picked my initial location as 1 meter. So based on these parameter values, I plotted x versus t and v versus t graphs, and now you will see them. So as you see, initially my location is 1 meter, and then it actually tends to 0 as time goes by. Initially velocity is 0, and then it picks up some speed. The system picks up some speed in the negative direction. It tends to go back to the equilibrium. It speeds up in the negative direction, and then it reaches a maximum, and then it also tends to 0. So finally the system stops. Okay? So since this is an overdamped system, we do not see any oscillations. So in our solution we do not have any sine or cosine functions. I hope this was helpful for you to understand overdamped systems. I hope you enjoyed the video. Please ask your questions in the comments. And if you want me to solve other types of problems, please mention them. And until next time, I hope you will have STEMtastic days. See you later, guys. Take care. Bye.